And welcome back to 16.4 where we're doing calculations on colligative properties. In this last section we're going to take a look at doing the actual calculations to determine what the freezing point depression and boiling point elevations would be for various solutions. Now just a reminder that what happens is when you add a solute to a solution, the vapor pressure lowers. And by lowering the vapor pressure, you have two effects. Number one, the the freezing point is going to be lowered, and in addition to that, the boiling point is going to be elevated. And so we want to actually calculate what those changes in temperature would be. So here's the equation that expresses the change in temperature of the freezing point when you add a particular solute. So you have the change in the temperature, which is delta T, and we have a little sub F there for freezing point. So this is the change in the freezing point temperature. And that's going to equal some constant Kf. That is called the freezing point constant. And then it's also multiplied by the molality. Now what is not shown here is what's also called the Van Hoff factor, I, which is approximately equal to the number of particles produced. By the solute. Alright, and so what's going to happen is, when we talked about this in 16.3, it's not the identity of the particles, it's the number of particles. So when you add solute that dissociate into a number of particles, you have to actually count up all the number of particles. Well, the Van Hoff factor, and that's what that is called, the Van Hoff, that's going to actually tell you approximately how many particles are being produced by the solute. Now the freezing point depression constant depends on the actual solvent that you're using. For example, water, which is the one that we're going to be using most common, has a freezing point depression constant of 1.86 degrees Celsius per mole. But here are some other ones that are just for reference. All right. Scrolling down, there's a separate equation, but very, very similar for the boiling point elevation, where the change in the boiling point is going to be equal to a boiling point elevation constant times the molality of the solution, and then once again times this Van Hoff factor. All right. There are separate values for Kb as opposed to Kf. There's the one for water, which is the most common one for us to use. So let's go ahead and try some of these calculations, and you'll see how this thing works. So the question says, antifreeze protects a car from freezing. It also protects it from overheating. Calculate the freezing point depression and the freezing point of a solution containing 100 grams of ethylene glycol in 0.500 kilograms of water. Alright, so this is freezing point depression. So you're going to use the equation where delta TF is going to equal Kf times the molality times this Van Hoff factor. So let's go ahead and take a look. We're dissolving this in water. So if you go back up, you'll notice that the freezing point depression for constant for water is 1.86. So we'll go ahead and plug that in. 1.86 times the molality of the solution. Well, we got to go ahead and calculate that molality. Molality is, again, moles of solute per kilogram of solvent. So we need to figure out how many moles of our solute that we have. 100 grams of ethylene glycol. And we actually calculated the molar mass of this thing previously. If I go ahead and scroll up just to remind you. The molar mass of the ethylene glycol. Nope, we didn't actually do it in that case. We did the ethanol. So we'll go ahead and calculate that real quick. Okay, so we have 2 carbons, 2 oxygens, and 6 hydrogens. So 2 times 12.01 plus 6 times 1.008 for the hydrogen plus the 2 oxygens at 16 apiece, and we get 62.07 grams per mole. So 1 mole of ethylene glycol has a mass of 62.07, and so therefore the number of moles would be 100 divided by that. 1.611 moles of ethylene glycol. The kilograms of solvent is already given. It's 0.5 kilograms of water. So we're going to have, this is going to be multiplied by 1.611 moles of solute per 0.500 kilograms of solvent. And so that is going to be our molality. The Van Hoff factor, excuse me, the Van Hoff factor for ethylene glycol is going to be a 1 because when you put this into water, it does not dissociate to any extent, and so we'll just put a 1 there. So to calculate the freezing point depression, we'll simply take the 1.86 times the 1.611 divided by 0.5 times 1, and we get 5.99. Oops. 5.99 degrees Celsius. Now, this is the freezing point depression. That's how many degrees the freezing point is depressed from the normal freezing point. And we know that water normally freezes at 0 degrees Celsius, and now it is being decreased by 5.99 degrees Celsius. So therefore, this particular solution will freeze at a negative 5.99 degrees Celsius. All right. Next one, what is the boiling point of a 1.5 molal sodium chloride solution? All right. So in this case, we're going to use the equation delta TB. The boiling point elevation will equal Kb, the boiling point elevation constant, times the molality, times the Van Hoff factor. And so let's go ahead and take a look at what these are. Well, the boiling point elevation constant, let's go ahead and scroll up here. The boiling point elevation constant for water is 0.512. And by the way, let me scroll up just for a second. We did forget a T in the Van Hoff factor, so let's just go ahead and correct that. So right here, and where did that go? Let's see if we can't try that again. And seems to be lagging behind here. There we go. This should be the Van Hoff factor with a T there, apostrophe T. Not a big deal, but we should be correct. Alright, so let's go ahead and move back down. We have a Kb value of 0.512 for water. Alright, sorry about that. It seemed to be a little glitch, but it seems to be fixed now. The freezing point depression constant is 0.512, which again, the units on that is degrees Celsius per molal. The molality of the solution is 1.50 molal. So these molals are going to divide out. And then the Van Hoff factor for sodium chloride is actually 2. This dissociates into sodium ions and chloride ions. So you actually produce 2 ions. So this Van Hoff factor is going to be approximately 2. It's actually a little bit less than that because some of these do stick together, and so you don't get completely 2 molecules or 2 ions for every sodium chloride, but it's close enough for right now. And so if we take 0.512 times 1.5 times 2, that's going to be 1.54 degrees Celsius. So that means that the temperature is going to be elevated from 100 degrees, which is the normal boiling point of water, by 1.54 degrees Celsius. And so in this case, the water will be boiling at 101.54 degrees Celsius. Alright, so given a particular molality, you should have an understanding what the Van Hoff factor represents. Given the boiling point or the freezing point depression constants, you should be able to calculate the change in temperatures, and as well as the final temperatures for the freezing or the boiling of a particular solution. Alright, that concludes Chapter 16.